Okay? So what we can do is we can say, okay, what does the association say between age and memory after I partial out or I remove the effect of speech? Well, that's over here, right? So when I actually say remove the effects of speech, you guys know how to do that already. So what I can do is if I remove the effect of speech from age, what I could do is I could regress age onto speech, right? From that regression equation, I would get a y hat or an age hat, right? And then I could subtract age hat from age observed to get a residual, right? That residual would essentially represent the area B and F. Right? So that what I've done is I've removed areas C and E from age. And then I can do the same thing with memory and speech. So if I were to remove the effect of speech from memory, I would remove C and D, right? Leaving ABF. Then the association between the pure association between age and memory would be A or B divided by A and B. Right? That's called a partial correlation. It's a partial correlation because we've removed the effect of the variables from both the predictor and the criterion. Right? The predictor is the thing that we're using to guess, and the criterion is the outcome of interest. So when we talk about these residual, these partial and semi-partial correlations, what we're really talking about is correlations between residuals. Right? And then it gets back to what you already know is just simple correlation. So all of this stuff is really, it's all the same stuff. Right? So what I'm going to do is we're going to go backwards today. Instead of doing this stuff by hand and then using the computer, we're going to use the computer, and then we're going to do stuff by hand to understand what the computer is actually doing, okay? Does that make sense to people? There's handouts. Okay. So the first thing that we can look at in our program, right, this is a stated program that we've written here, is that one thing that you'll notice is that I have what's referred to as a header in my program, all right? First thing we see is what's the file name, who wrote it, what's the purpose of the file, right? That's something that we talked about before that we should do every time we write a script, we write a program. Okay. All right, so the first thing I'm going to do are things that you've seen before, nothing terribly new. So I'm going to clear memory and input the data into Stata. We'll do it this way. All right. Now, if I want to get partial and semi-partial correlations, quite honestly, I don't know of any other computer program that does it easier for you than Stata. So to get the partial, the first thing I'm going to do is I'm going to look at the zero order correlation. So let's look at that, and then we'll see what happens. Because this is going to be an interesting story.
What does zero order correlation mean?
Okay, zero order correlations are the simple bivariate. Did you ask the question? Oh, you did. It's just the correlation, the bivariate correlation between the raw variables. I haven't done anything to them yet.
Okay.
Okay. So, we're looking at, we're interested in looking at the relationship between age and memory and speech and memory. In this case, memory span is the outcome of interest, right? So ignoring the other variables, the relationship between age and memory is what?
0.75.
So it's a positive relationship, and I could square that 75 value, right? That 0.75, and what would I get? That's called a coefficient of determination, right? And so what's 0.75 squared?
What
What's the PW before forward?
This is pairwise.
Pairwise.
Pairwise, and I have to do that if I want to get the statistical significance.
So it's 0.5625.
0.56. Right, so that we would say that the relationship between age and memory is positive. Right, the relationship between age and memory is positive. And age can predict 56% of the variability in memory span. Right, so that's that interpretation. And the same thing for speech. Who wants to take a crack at that? So the first thing we can say is we can look at the sign of the correlation coefficient. So if you guys haven't seen this before, the top number is the correlation, the bottom number here is the p-value. Okay. So we have 989. I'm just going to call that 99. So what happens when I square 99?
0.98.
Point
98.
Right. So how would we interpret the relationship between memory and speech?
It's positive correlation and the variability in speech predicts 98% of the variability in memory.
Or 90% of the variability,
90%.
right? Okay. Okay. So let's keep that in mind. So instead of going through a lot of rigmarole to sort of see how these partial and semi-partial correlations are computed, I'm simply going to use the data command pcore, partial correlation. So when I look at this is my y variable. The first thing it's going to be pcore, that's the command. This is my y variable. And then everything after the y variable will be my predictors. Okay, that's how we interpret that. So let's take these in turn. Let's take these in turn. So the first thing we're going to look at is we're going to look at the relationship between age and memory holding speech constant. Right? So a lot of times in regression you'll hear that kind of language. Right? Holding everything constant, the relationship between age and speech are these things. Right? So here I have this coefficient for a partial correlation. How would I interpret that value?
So if speech weren't part of the relationship, then age would have a negative relationship with memory.
So it's not quite right to say if it's not part of the relationship because we're acknowledging it's part of the relationship.
Holding it constant.
So after we've removed the effect of, the look on your face is priceless because you're looking at this trying to make sense of it, aren't you?
Yeah.
Yeah, that's why I chose these data. So when we remove the effect of speech from both age and memory span, right? The relationship between age and memory span completely changes. It completely changes. Right? So this is what we can say about the unique relationship between age and memory span. The unique relationship between age and memory span, so on the front of your sheet here, that unique relationship would be that area B divided by the area A plus B. Right? Because we have removed the effective speech rate from both of those variables. So B becomes the unique relationship between age and memory span after we remove the effective speech rate. This is what happens often when we hold things constant. Relationships that we see in a univariate sense get all topsy-turvy and goofy. Right? So it's important to not be enamored with these univariate statistics. Right? Because if you think of the world as a complex set of systems, or a complex system where things are constantly interacting with each other, right? It may be too simplistic to look at simple relationships, because simple relationships don't often tell the real story of what's going on in the world. So by using these methods, we can begin to describe how all of these variables are working together in concert. Right? So when I square this partial correlation, so this is my partial correlation squared. So the partial RxY squared for this then becomes 0.25. So I go from a zero order correlation, coefficient of determination of 56, which that's pretty promising, right? That's pretty promising. To when I remove the effect of another variable or sets of variables, that relationship shrinks. It's going to shrink tremendously. Okay.
Can you just go through again so the way that you set it up, the P4 memory, age, speech, how does it know which one to remove?
Okay. So what will happen is that for memory, we're calling that our outcome variable.
Mm-hmm.
Right? If I had variables A, B, C, D, E, F, and G, what it's going to do for a partial correlation, for my A variable, it's going to remove the effect of variables B, C, and D from both memory and variable A. And then it's going to do the same thing for B. It's going to remove the effect of A, C, and D from memory and variable B. So it does it in a stepwise fashion. That's the advantage of using the command this way. It does it all for you.
And that, if you just wanted to look at the relationship between age and speech without memory.
Age and speech, yeah, we did that already. We did that with the zero order correlation.
Or, if you wanted to take one of the variables out, could you just do correlation of the two and just leave the third one out?
So if you just wanted to look at the relationship between age and speech, ignoring memory, that's a bivariate correlation.
Okay.
That's a simple bivariate correlation. If we wanted to look at the relationship between age and speech, controlling for memory, we would have to, choose what our outcome is, right? Is age the Y variable? In which case we would just swap these.
I think this might just be completely stupid, and
no
everyone
one
else might completely understand this, but I think I just am not quite sure what it really means to control for memory. It's I always just, I know that we talked
we're
about
not controlling
that,
for memory in this case.
Okay.
In the way that we've written this up, we're interested in memory. We're interested in the relationship between memory as the outcome and other predictors. Right? So in this case, this is the outcome. These are the predictors. These partials and semi-partials allow us to describe the relationship between each of the predictors and its unique relationship with the outcome. So when we say unique relationship, we're going to talk about partial and semi-partial correlations.
Can you help put into words what this means about the relationship between age and memory, and then review control for speech, and the fact that it draws sort of implied this, and then
okay, so
and then I'm just trying
to conceptualize it. Do you have
regular words?
Regular words.
Yeah,
Do you
I
have,
can see how it changes, but then, like you were running up your,
do you have the Venn diagram?
yeah.
Okay, so look at the Venn diagram. So what we looked at, this negative point, this 0.25, this 0.25 here, if I were to write a number here, B actually does equal 0.25. How I computed B from looking at the diagram would be B divided by A plus B. So I can talk about this squared partial correlation as the unique proportion of variance shared between age and speech, between age and memory, after removing or holding constant the effect of speech from both age and memory. That has a little bit less intuitive interpretation than does the semi-partial. Because when we think about our outcomes, we don't think about part of an outcome. We think about what is the unique relationship of this variable and the outcome. Okay? Which is what a semi-partial does. So this becomes the semi-partial correlation. So the semi-partial correlation is the relationship between age and memory holding speech constant. So in that case, when we do a semi-partial correlation, we're going to leave memory intact. So that's going to, the variance of memory is going to be A, B, C, D in the Venn diagram. And then we're going to remove the effect of speech only from age. Right? So in the Venn diagram here, what we have done is that we've removed areas C and E from age. Right? We've removed C and E from age, but we allowed memory to stay intact. So that being said, we can then interpret this semi-partial R squared.
Wait,
Yeah.
If that memory's intact, we remove C also?
Pardon?
C is part of memory also.
Yeah, but we're going to leave that intact.
So we remove C adding or just E?
We're going to remove C only from age, but leave it in memory. Memory stays the same.
But if partially you remove it from both?
In a partial, we remove it from both. In semi, which means half, you're only going to remove it from half of the equation. That's maybe an easier way to remember that. Okay? So the semi-partial correlation goes, that's kind of a, that's close to zero. Right? Right? So I can think of this semi-partial correlation between age and memory, holding speech constant, as the incremental amount of variability, or the amount of variability, or if I were to square this, this is the incremental amount of variance that age predicts in memory above and beyond what speech explains. All right, so I've left memory intact. So I can talk about memory as a whole variable, all of the variance in memory. And how much of the variability in memory does age explain above and beyond speech? Well, speech is going to explain C and D divided by A, B, C, D, right? And the unique proportion of variance that age explains above and beyond speech is this little area B, right? Because this area B here does not belong to speech at all. So this would be B divided by A, B, C, D, right? Make sense? In fact, when we do regression, multiple regression, this is what we're talking about. We're really talking about, in some sense, semi-partial correlations.
Do we ever use partial correlation?
There are some situations where you might use that. It's rare. In medicine, I can't think of any particular situations where it would be intuitive to use that. And certainly in policy research, I wouldn't, because it's too confusing, right?
So I think I'm like almost there, but can you just tell me the letters for the semi-partial?
Yep, okay.
Again, so I can write it down.
Okay, so the semi-partial correlation, first of all, semi means it's going to take it out of
The predictor.
just the predictor. So the semi-partial correlation is going to be B, right, over all of the variance of Y. All right, so semi-partial, what have I done? I have removed the effect of speech only from age. So I've removed the E and C from age, leaving the only thing left between age and memory would be B. This is the incremental effect of age. You don't get credit for C.
And then partial, you're removing from both.
For partial, what I would do is I'm going to remove it from both. So the relationship looks like that. So I'm going to correlate age prime with memory prime. In this case, it's going to be B, because that's the overlap, divided by whatever's left over of memory after removing the effect of speech. So that's AB. So really, we think about these, it's just nothing more than correlations with residuals. Right?
So just for example, to make sure I sort of understand, like if you're going to go the other way, like when you speech,
Okay.
like a semi-partial with speech and memory, it
Yeah.
would be D over A, B, C, D, and then a partial would just be D over A plus D.
Yeah.
Okay.
Say that again?
So like a semi-partial would be D
D.
over A, B, C, D.
Yes.
And a partial would be D over A plus D.
Yes.
Okay.
That's exactly it. Yeah. But the idea here is again, you think about it, if it's semi-partial, I'm only going to remove it from one. What is the incremental variance that the variable of interest that we're talking about shares with the outcome, right? That's the incremental variance.
So regression is really a bunch of semi-partial
Yeah.
correlations.
Yeah.
And practically, do you ever use the partial correlations?
It's often a personal preference.
Okay.
My issue with using partial correlations is trying to explain it to lay people.
Okay. Right.
That becomes very difficult. What do you mean I've removed the effect of something from the outcome? Right? So, so what we can say when we do these semi-partial is, let's say I had age, speech, weight, IQ, all these other variables. What we could then say with respect to the semi-partial correlation is, if all those other variables were equal, if I had two people of equal age, IQ, the effect of age on memory would be whatever it is. And that's how we tend to refer to, or how we interpret regression coefficients.
So does the significance value that's up there reflect either the partial or the semi-partial?
They're both. It reflects both. So the significance, the statistical significance of this partial and this semi-partial is 39. And the statistical significance for this partial and this semi-partial is 0.03. Because it's the same thing. Right? Same thing. If I were to do a regression where I included age and speech to predict memory, these are going to look familiar to you. Sorry.
And the first, when you did the zero order, that's just not taking anything.
Nope,
You're
it's
looking
just-
at age and memory, but you're not excluding.
Not doing anything.
at all.
Yep. So think
What is
about,
that?
huh?
Like, what's the,
Well, that's to help teach something.
okay.
Because let's say that you're interested in building a model where you want to predict something, And let's say that in this case, you omitted speech. What would your inference be regarding the relationship between age and memory? Well, you ignored it. You didn't include it. Remember last time we talked about thinking about what variables we want to include and how we want to treat them? What would happen if you omitted speech in your model?
Then it would look like age and a bigger question.
It has so remember we talked about Simpson's paradox? When we drew Simpson's paradox with respect to the assumptions of the correlation coefficient? Remember this? Simpson's paradox. In the case of Simpson's paradox, not only do we get the strength of the relationship wrong, but the direction of the relationship is wrong too. So if we omitted speech when we were investigating the effect of age on memory span, our inference would be that the relationship between age and memory is positive, and if I were to square it, it would have this, if I may, a relatively strong association. Is that a proper inference? No. It's a complete. So in that sense, if I omit variables in my model is wrong. My models are biased, which introduces us to another assumption, or assumption that is going to be unique to multivariable regression. And that additional assumption in multivariable regression is you have included all relevant variables in the model. Because if you don't include all relevant variables in the model, this can happen, this Simpson's paradox thing. So this is, that's why I took the time to draw all these out, right? To sort of tell that story. Which is kind of important if we're trying to make, if we're trying to describe the world and make predictions and things like that. If we omit an important variable, then we could be way off in describing the world. Does that make sense? Okay. All right, that's the easy way to do the partial and semi-partial correlations using the p-core command, right? It's a very simple way to do it. So again, if we can think of these partials and semi-partials as nothing more than correlations between residuals, it renders that, see the formula there on this first page, which is all but unreadable and incomprehensible, right? You don't need to do that, right? Before we had high-speed computers, this is how we actually had to do things, because the algebra was too tedious to do it the other way. But if we can think of things as residuals, then we can use things that we already know to be able to compute things differently. So here's what I'm going to do. I'm going to start doing a couple of bivariate regressions, right? I'm going to start doing some bivariate regressions, and from those regressions, I'm going to want to get the residuals, okay? So my first regression is I'm going to regress memory, my outcome, onto age, right? And then what I'm going to do is I'm going to use the state of command predict to get two variables. Now, if I do predict, and then this thing after predict is going to create a new variable. This new variable that's going to be created is called memory hat. So memory hat, if I put a hat on something, that means it's a predicted value, right? So this is going to be my predicted value of memory, predicted from age. Now, I'm also interested in the residual, whatever's left over from that prediction, right? So to get those residuals so that I can then correlate residuals, I just do predict a new variable name, residuals.
If you do predict memory hat, how does it know what it's assigning that?
It's smart enough to remember that the previous command was a regression command, and it's going to basically do the arithmetic for you to get the predicted value. So if I don't give it any options, its default behavior is to come up with the predicted value.
Okay. So it doesn't actually matter what you're calling it, it's just because you do predict after regressive.
Yeah. I could call it, Wilma, or Dino, or Pebbles. All right.
And then what was the second one? The mem age residuals?
Yeah, I could have called this thing anything I wanted. It's just what I want to know is, I named it this way. I know this is the residual after regressing memory onto age. Otherwise, I would get confused later on when I begin to use these things. You could call it whatever you want. Right? And it's actually going to create new variables. All right. So let's do that regression command. Right. Nothing new, nothing that we haven't seen before. This is our ANOVA table. Tells us the number of observations. Okay. Incidentally, does anybody remember what the bivariate correlation was, or the p-value for that bivariate correlation between age and memory? It was this. That's because it's all the same. It's all the same stuff. And if I were to divide 16 into 9, I would get that r squared of 56, because it's all the same. All the same. All right. Okay, well that's not interesting. This is what I'm not interested, but this is what I would need to do to get these residuals. All right. So then the other thing I want you to notice here is, keep your eye on this the variable list here. After I run the predict commands, these new variables then get created. Okay? So just again, to give you that intuition as to what these things are doing, this is the predicted value, this is the residual. If I were to add these two together, this is going to get the observed value. Right? This is the observed value. Right, so does everybody understand predicted value, residual? Right? Okay. So let's do a couple of things here before we go on to before we begin to start correlating our residuals. So one thing I want to do, is what do you think would happen? What do you think would happen if I correlated age and the predicted value of memory based on age? All right, so what that would look like is I have age, right, and then I have memory. And remember now, this line, this regression line is really memory hat. So what do you think that correlation is going to be between the predictor and the predicted value? It's going to be 1. It's going to be able to predict that perfectly. Right? Right? And then the residuals are these values here, right? It's the distance and direction from with respect to the observed and the predicted value, the expected value, right? Something that you've been doing probably since your second day in statistics. These are the residuals, the deviance, the error. Now, if we define error as the stuff left over, it's the variance that the predictor doesn't explain. What do you think would happen if I correlate the residuals with the predictor? All right? Any think about it. From the Venn diagram, right, we're going to correlate age. First of all, which portion of which, if I were to look at the relationship between age and memory, I'm talking about BC over ABCD, right? Right? So the predicted part would be BC, right? What's left over is AD. That's the residual from that regression, right? So what would happen if I regressed or correlated AD with BCFE? Is there any overlap? Is there any relationship between AD and FBCE? No. So the relationship between that residual and its predictor is going to be 0. Right? The reason I'm spending a little bit of time on this is I want you guys to really understand what it means to residualize something. We have literally subtracted that variance away from the variable that can be explained from the predictor. So anything that's left over, the residual or residue or whatever, that's got nothing to do with the predictor. It is completely independent. And if you remember when we were doing R squares before, we did something like this. Right? So this becomes our predicted value with a hat, and these are our residuals. And so we have to intuit what these residuals are. It's leftover stuff. It's leftover stuff. Okay. And then I'm just going to do the same thing. I'm just going to do a whole bunch of bivariate regressions here and get a whole bunch of other residuals. Okay? So this one is going to be the residual of memory after removing the effect of speech. This will be the residual of age after removing the effect of speech. This is the residual of speech after removing the effect from age. Right? So now, if I'm not interested in, saying one is a y variable, like I've drawn on the Valentine here, I can now look at partial and semi-partial correlations amongst all 3 variables. Okay. So is everyone with me with what we've done and understand what we've done by doing the regression and then getting the residuals from those regressions? We got the leftovers. And when we're looking at partial and semi-partial correlations, we're interested in correlating leftovers. So let's call this day after Thanksgiving statistics. That would be a great time to do this, like the lecture after Thanksgiving. Right? Okay. So all I'm going to do now is to get the partials, as I'm going to simply correlate the residuals. So I'm going to correlate memory after I have removed the effect of speech from it. And then I'm going to correlate that with age after I've removed the effect of speech from that. Right? So back on the Venn diagram, the variability here, mem sp, is AB, and age sp is going to be BF. Does that make sense? Because we have removed C, D, and E from those variables. Right? And then we'll do the same thing for the other set. Right? So if I compare these values with what we had before, they agree. Right? That's what a... Right? So I'm going to show you a couple of different ways to get you an intuition as to what this thing is doing. Okay, does everyone see how this is the same thing? We simply correlated the residuals.
Is it just more a roundabout way of getting at the same
thing? Yeah, yes. The reason for that is if I just use the command, you may not get the intuition. If I talk about Venn diagrams, some people may not get the intuition. So I'm trying to present it a couple of different ways so that you get it. And maybe if you try and explain it to somebody, they don't get it. Well, how about this way? How about that way? How about this way?
You're just trying to say that it's like correlating individuals.
That's all it is. That's all it is.
Can you just say one more time, like the variables, mem underscore speech, age underscore speech,
Okay.
where they are on the Venn diagram?
Yeah, okay. So let's take it from the top. So if I look at mem age, this is memory after I've removed the effect of age from it. So that's going to be AD, right? So you tell me, this is memory, the residual of memory after I've removed the effect of speech. So what's that going to be?
A plus B.
A plus B. Good. Age speech is what's left over from age after I've removed the effect of speech from it. So that's going to be BF. And then this is speech after I have residualized age from it. DG. Right? See, you guys got this. See, this is why you guys are a pleasure to teach. We were on the elevator this morning. She's like, you guys hate me. Or you hate us, right? Because I didn't show up yesterday. It wasn't on our calendar. I'm like, no. I love you guys because you guys get this stuff. You don't think you get it.
No, we don't.
You don't think you get it, but compared to the thousands of other students I teach, you guys are awesome.
The questions you ask show a level of understanding that we don't usually see.
So if you really want to piss Tom off, just randomly go,
What?
what?
Like, as we put something up on the screen, actually, you know what? Ask about the bottom here while we're talking about correlations. Ask about this part right here, and then when we're done, after I've gone all the way through this, then ask about these comments at the beginning.
All right. Okay, so you got that right. The partials are correlations of residuals. That's it. It's very simple if you break it down into its atomic components. The semi-partials are just as intuitive when we break it down in its component parts. So here, to get the semi-partials, I'm going to leave my outcome intact. I'm not going to look at any residualized memory. I'm going to keep memory intact. So memory is ABCD in the Venn diagram. So I'm going to correlate ABCD with age after I've removed the effect of speech from it. So what I'm really going to do is I'm going to correlate ABCD with what?
F.
BF.
BF.
Right? Does that make sense? Mm-hmm. And then what am I going to do when I do the semi-partial between memory and residualized speech after removing the effect of age? What's that going to be? With
DG.
With DG, right? This would have taken 6 weeks in another class. What? What? Yeah, okay. What?
So the correlation is these like I guess what I'm trying to understand is what are the things that are just A plus B?
Those are squared. Those are squared because that refers to variance, right?
Okay.
So if these are correlations,
yeah,
we have to square them to get the variances, right? So if I square this -0.07, it gets down to this teeny tiny 0.005 value here. Mm-hmm. So that is literally what B divided by ABCD is. Because those are that's variance. Okay? So you guys see it. It's stuff that you already know. Right? It's stuff that it's right. And all we're doing is we're doing some stuff to the data, and then we're going back to bivariate statistics. Even though we're talking about multivariable regression, it all gets back to simple bivariate correlation. So when you start getting like, oh my God, this stuff is really complicated, it all gets back to something that is very, very simple. And you've been doing it, probably looking at it for a very long time, and really do understand, right? So take your time and remind yourself that it's really the same stuff, that it's simple stuff.
If I wanted to, like the semi-partials, so I understand like you can take the effect of speech out of age and then correlate age with memory.
Yes.
Can I take multiple extraneous variables out
Yes.
of age?
Yes, and that's what multiple regression is. But the process would be exactly the same. The process would be exactly the same. Right? We just, if I had more variables, it would just be more confusing. But the concept is exactly the same. Okay? Yes?
This is my, where did the F go? In the Venn diagram, you just said that we're gonna
Oh.
do B and F correlated with A, B, C, D.
Right, and I said that the squared value here is really this. Well,
Where did the F part of the age go?
it's still there, but this 0054 represents ABCD divided, or B divided by ABCD. So I've left memory intact, and I've correlated age prime with all of memory. So that F area, it would be, if I were to do a regression, would be the residual between the relationship between age prime and memory.
And H prime.
So when I say prime, I'm talking about that's the residualized variable. The residual, right?
Okay.
So like each prime is like the age underscore SP.
Yes.
Sorry, so those formulas like the B over A plus B plus B plus B correlating to the R squared.
R squares, because that's really what we're
And
interested
B over
in.
A plus B is the R squared.
Yeah, those are R squares, yes. Because we wrote it down in terms of sums of squares and things like that. Okay, all right.
Do you know in general literature, do they use partial, semi-partials or partials?
Very well in
Seems like semi-partials.
semi-partials. Semi-partials tend to rule. That will vary on disciplines, but in what you guys are likely to read, it's going to be semi-partials.
Because that's what regression is, right?
Yeah.
Just a bunch of
Yeah.
semi-partial correlations.
Again, try and communicate a residualized outcome. People go, oh, that's statistics.
Right.
You statisticians are crazy. It's more intuitive. Okay. So we've done that, and right, so you guys sort of get this, right? It's not that difficult. It really gets back to simple bivariate correlation, right? So I'm going to do another thing. So we're going to do our first multiple regression. All right? Hold on your hats. It's really hard. All right, one more regression. And now what I'm going to do is I'm going to fit what I would refer to as my full model. So now I'm going to regress memory on both age and speech simultaneously. This is multiple regression. It's that simple in R. All right? Okay. So here's what I want you to take away from this little exercise here. I don't want to get into multiple regression yet. But there's a third way to get at these semi-partials, which I think will make the interpretation rock solid, crystal clear. Okay? Okay. So this model, this regression model, has a multiple R squared. Right? It's the same interpretation as you've been doing forever and ever and ever. How would I interpret this multiple R squared of 0.9835? Which, by the way, if you look at the bottom of the code, you'll see 0.9835. That's where I got that from. That's that multiple R squared from the final regression model. How would you interpret that?
Is that the joint effect that age and speech explain 98%?
Yeah. Yeah, that's the combined, that's the total variance that your model explains. It's just a more sophisticated model than a bivariate model. But in the end, if we were to write down the model, right? Right? This is what we've been dealing with for a long time now. The only thing that's different from this model than what we've written from a bivariate model is I've now added a beta 2. That's the only thing that's different. But this component becomes our expected value. Right? So just like on the first day we did this, this is just a generalization of this, and then we did this. I can also do this. It's the same thing, right? So what happens here is that these things combine to create one variable. They combine to create one variable, and then this simplifies to that concept. And then this r squared becomes the bivariate correlation between this value and this value. It really does simplify to the easiest case. That's it. It's not that difficult.
Can I ask a question? So, I feel like the doctors in medical journals and the people that don't understand statistics that well, they kind of, the way that I've been taught this is that you basically do the univariate regressions, and then you just choose whatever seems significant, and everyone just jumps to the multivariate without thinking about partial or semi-partials. Like, I'm assuming that's dangerous, but then are you going to tell us which times that's dangerous?
It's dangerous all the time. Because what can happen is that one variable and another variable can be very poorly associated. But that other variable combined with other variables can create a linear combination that becomes very powerful. And that's why I did the zero order correlations, and then I did the residuals to show you what the problem or what the potential problems of interpreting those. I'm going to do the bivariates and choose from there. Because you would have chosen age and said, oh, age, really strong predictor, when in the end, speech dominates that relationship between memory and speech, right? Right? That's ancient, old school, 1920s, 1930s statistical techniques.
So the take home, like, you can't tell us what to put in the model.
Right.
We have to have a really good conceptual framework to build our own model. You can't just kind of fish like that.
Right.
So like when you're going in, you have the variable that you know you have. You should actually thinking about it and not just
There's that word. There's that word. Remember I talked about that on Tuesday.
Like I'm trying to, is that like so like we're getting back to like totally non-statistical things, right? Okay.
But it's really disconcerting because what it's making me think is that in any relationship that I'm trying to examine, that there may be a speech type variable that I'm not thinking about.
Yep.
There could always be variables that might be dominating a relationship that I'm misinterpreting.
Except for one case.
You want to stop doing all of it.
Except for one case. Can you think of the one case where you don't have to worry about those other variables? A randomized trial.
Because
That's
it
the
separates
power.
it separates the circles in the Venn diagram.
By
So you don't
design.
have all the...
Yeah, it separates it in the sense that it looks like this. If this is y, this is x1, this is x2. x1 and x2 won't be correlated.
Right.
Right? There's no C, there's no intersection between the three variables, which makes the interpretation of your data crisp, clean, and efficient. That's why statisticians harp on the power or the quality of the evidence that come from randomized clinical trials. Because you don't have to think about these things.
Unless there's another circle that just circles x1.
It wouldn't matter because x1, these are treatment variables. They're made up based on what? What is the process that gave rise to x1 and x2? In a I'll give you a hint, randomized clinical trial.
Right, but that's assuming your randomization worked. But
Randomization always works.
as long as you have the right size.
Randomization always works. This gets back to the concept of a sampling distribution. right? If I were to do a random, let's pick a small sample size. This is the sampling distribution of sample size 4, right? What's going to happen is that this distribution is still going to be centered around theta, whatever the real number is, right? But it could be, you know, really large negative or really large positive. As my sample size increases, the distribution is going to look more like this. It's still going to be centered around theta, but because my sample size is large, it's less likely that I'm going to get a really bizarre result. But in the end, if I were to repeat these samples, these randomized experiments where sample size 4, on average, I'll get the right answer. Randomization never fails. You can't have bad randomization. It's random. Just, you know, it's just an implausible or an unlikely randomization. But it's still random. That's the other thing that the medical literature perpetuates, is this idea about the randomization failed. Really? No. People who talk like that haven't yet grasped the central limit theorem.
Thank you.
Which is why you never trust the results of a single study. Okay, all right, where the hell were we? Oh, right. This is the R squared from the full model, okay? So if we were to think about the semi-partial as sort of the incremental variance that a variable adds above and beyond what has been added already from previous models. Thanks. I'm going to go back up top to our bivariate regressions. Here somewhere. So this is the R squared when I regress speech onto memory. This gives me an R squared of 9780. Somebody want to do that calculation for me? Does that sound familiar?
Wait, what are you doing? Where are those coming from?
Right, hold on. What happens when I subtract the R squared when I residualize, not agent speech, that's the wrong one. Is it agent? Yeah, agent speech. Is it agent speech? No, that's not right.
Must be memory and
Memory age.
memory and age.
Where did it go? Oh, wait. Memory age. Did I not do it? All right, well, let me do it.
Memory speech.
I must have done
Memory
the
age.
variables there.
Memory age is 0.5625.
Say again?
Memory age was 0.5625.
All right. Thank you. 0.526.
5625.
That's dyslexic because I'm okay. What does that give me?
I'm gonna guess 0.421.
Now let's go back to that partial correlation table that we created. So these become the squared Semi-partial correlations. Right? Does that make sense? That doesn't make any sense? Did I just confuse you?
Where did those
Okay.
numbers come from? 9, 8, 3, 5.
Let's do this. So this is the R squared from the full model. This is the R squared when we had age and speech predicting memory. Okay? That 9, 8, 70, does anybody remember where that came from?
That's the R squared for memory and speech.
Memory and speech, right? So what I have done, if this is the amount of variability that a speech predicts in memory, this difference must be what? That's the incremental effect of age. This is the effect of age above and beyond what speech has already predicted, which is the exact interpretation of our semi-partial R squared. Got it? This 5625 is the R squared from the model where I predicted memory from age. Right? So if I subtract out the variability that from memory that age already predicts, this is what's left over from the joint prediction. This I can then interpret as the incremental effect of
speech
after controlling for
age.
age. Right? It's just correlations. It's just correlations. What do you think?
Some people refer to thinking of incremental R squared.
Yep. Incremental R squared. Yep. Okay. Some people, just to confuse you, will call semi-partial correlations part correlations. I don't know why. If you're an SPSS user, it calls it, excuse me, it refers to semi-partial correlations as part correlations. Yeah? Okay. All right, so there's probably a homework in the future, right? So take some variables from the PQuAS data set and do this. You can take the shortcut, use the pcore command. What I'd really like you to do is practice writing down the interpretation of these statistics, all right? Because then that's really the hard part. I mean, it's simple to type in the commands. The intellectual capacity comes in with the interpretation.
So take 2 variables and do this?
You need
or
3.
Yeah, 3 variables and do this.
Right. And if you, she asked if you, what happens if we added more? If you want to add a whole bunch of them, add a whole bunch of them and see what happens and see if you can try and interpret that. All right, so through no fault of you, we have to do something to make up some of the time that we missed for the Stata class. So what I don't know if you've noticed or not, but I'm trying to incorporate more Stata into this class than probably what you had in the previous in intro. So my goal then to get you guys up to speed is to do lots more of that and talk to you guys about other options. I know Andy's class doesn't start till 10:30. We usually go late anyway. So, but I'm concerned about, giving you guys a break, go to the bathroom, make phone calls, check emails or something like that. So a couple of options that I have, off the top of my head come up with. Well, one, we're going to incorporate Stata code more and more into the classroom. So what that means on Thursdays, bring your computers, because Thursday will be practical day. But the other thing that we can do is between now and the end of the semester, we can just continue to add 10 minutes to the end of every class. If that's not good, and I say no, okay, never mind. There are other Wednesdays that are available. So instead of having these once a month, which quite frankly, if we were to keep it that schedule, you lost everything that we did the previous month anyway.
Yeah. We had changed it to every 2 weeks. And that was the plan.
That was going to be for next year.
That's why we changed those dates.
Okay.
And maybe why you missed it. Because
Didn't. Okay.
it's probably in the inbox.
I think it makes sense the way you're doing it. It makes so much easier as you teach us the concepts to show us them to see it.
Yeah, okay. So how about this? I'll work with Elliot to figure out, you know, because I know you guys have other lectures and other people coming in on Wednesdays is sort of like, you know, potpourri day for you guys. Wednesday at 2:30 to 4 or whatever, yeah? 2:30 to 3 or whatever it is.
I don't know. In general, Wednesday 2:30 to 4 is for STATA, and the other things come before 2:30. Am I wrong?
Yeah, normally
we
we have instant things from 12 to 1 or 1 to 2. But they
Yeah, and then after that, it's usually
True. We don't usually have anything after 2:30.
Yeah, it's usually
True.
Okay. I'm going to double check with Elliot to make sure there's nothing conflicting. And then we will post a schedule which will meet more frequently and actually meet on those days. Is that amenable to everybody? Yes? Okay. Okay. But everyone understand partials, semi-partials, and what to do next for your homework?
Yeah.
Okay, all right.
What did I just say was like